Have you ever wondered why you're here? What led to our position and the potential for the development of humanity? How did everything align just right so that we had matter and forces and that everything came into existence? Welcome to today's video, which is going to be all about the formation of the universe. We will be going through the what, when, and whys through this presentation. But before we begin, please like, follow, and share this video in order to support my personal project. There are many theories regarding the formation of the universe. There is the Big Bang Theory, which is the most widely accepted theorem today, and the one that we will be discussing in this video. There is the Steady State Theory, which states that the universe is undergoing constant expansion, but constant average density is maintained. Therefore, matter is continuously being created. There's also the Multiverse Theory, which discusses the existence of different configurations or variations of our universe. Then there's also the String Theory and M-Theory, which is for another later video. And then there is the Cyclic Universe Theory, which promotes the idea of a continuous cycle of expansion and cooling. The Big Bang Theory says that all matter found in the universe was created 13 billion years ago in a state of an incredibly high temperature and density point, known as a singularity. The singularity is the point at which the physical laws we are accustomed with are no longer applicable, and temperatures and densities go towards infinity. All of this while being considerably smaller than an atom. Why this singularity occurs is unknown. This is a condensed and only partial timeline of the universe. The actual and complete one would take a whole lot longer to get through, while this video is meant to give you a relatively brief but cohesive overview. Without further ado, to begin, we have the Planck epoch, from 0 to 10 to the negative 43 seconds, which is when things were starting to become interesting. The universe was just hot and dense enough that the four fundamental forces, strong and weak nuclear force, gravitational, and electromagnetic, were one. This was then swiftly followed by the grand unification epoch from 10 to the negative 42 to 10 to the negative 36 seconds. During this time, after being so incredibly hot, things began to finally cool down and the forces were separate. Subatomic particles like quarks, leptons, and force-carrying bosons were created. Then came the inflationary epoch from 10 to the negative 36 to 10 to the negative 32. Everything expanded. This is called cosmic inflation. During this time, the universe expanded faster than the speed of light, and exponentially so. Then there was the electroweak epoch from 10 to the negative 36 to 10 to the negative 12. Strong nuclear force is separating from the others and interactions between two form, as well as the W, Z, and Higgs bosons. The Higgs boson is relevant because it gives mass. Suddenly, the universe can now support things with mass, and things are starting to finally gain that property. Then there is the quark epoch, from 10 to the negative 12 to 10 to the negative 6 seconds. As everything cooled, baryons would form, such as protons and neutrons, in greater quantities. Any quarks and their respective antiquarks would cancel each other out. However, since there are more quarks remaining, this resulted in the formation of matter. Then, almost last but not least at all, is the hadron epoch, from 10 to the negative 6 to 1 second. Finally, a time that we can measure on a stopwatch. The temperature is down to approximately 1 trillion degrees Celsius, which is the ideal temperature for hadrons to begin to form. Pairs of oppositely charged particles are beginning to form as well, in combinations to ensure that the energy and the mass is being conserved. Then there is the nucleosynthesis, which occurred from 3 minutes to 20 minutes, when the nucleus of an atom can begin to form via nuclear fusions. So that is when we start seeing elements like hydrogen, helium, and lithium. Stars and galaxies began to form 300 to 500 million years down the line. Our solar system, as we know and love it, began forming 8.5 to 9 billion years down the line, and now at 13.7 billion years since time became a thing. The universe is continuing to expand, and star materials from old dead stars are being reused to make new stars. Light needs time to travel. What we see when we observe space is not the current state of things, rather what they were like at a certain point in time. It takes 1.3 seconds for light to travel from the Earth to the Moon. To reach the Sun, it takes 8 minutes. Therefore, all imagery we get experiences some sort of delay. Therefore, if we look far enough back into the past, we should see the remnants of the Big Bang, and we do in fact. This is cosmic microwave background radiation. It is the remaining initial light that first ever traveled through the universe. Two astronomers named Penzias and Wilson first discovered a signal that couldn't be identified in their radio telescope, and it came from everywhere with the same metrics from all around. They deduced that it must have been emitted from something outside of our own galaxy, as it wasn't affected by any nearby occurrences. Due to the longer wavelength of this radiation, it can only be detected by equipment like the European Space Agency's Planck mission. This light was all released before the universe became opaque, during a period of time when matter was almost only made up of neutrons, protons, and electrons, and the latter interfered with the photons, and therefore limited the movement of light. We know that this radiation is from the time of the formation of the universe because of its uniform nature. The temperature of all recorded areas is so similar to one another that there is no other event that could justify such an even release of heat. All atoms and all light make up under 5% of the cosmos. So, what else is there? Dark matter is invisible. Light passes through it as such. However, it has an influence on gravity, and therefore it must have mass. This is suspected to be some undiscovered subatomic fundamental particle. When we observe stars and galaxies in movement, what we observe is more than what it should be. There is some particle that is clearly missing. The current belief is that the universe will continue expanding and cooling down to a point where it will be too cold to sustain life and even reach absolute 0 Kelvin, which is negative 273.15 degrees Celsius or negative 460 degrees Fahrenheit. At this temperature, there is no more motion or heat. Everything just stops. This is known as the heat death. It is also worth noting that the rate of the expansion of the universe has been increasing. This was determined through the observation of distant supernovas. Supernovas are exploding stars, a process with a significant energy release, therefore resulting in the possibility for detection. All stars that become a certain measurable type of supernova have the same starting mass. Therefore, the explosions release the same amount of energy. The only difference is our perception of the light emitted, the brightness, due to their distance from us. The supernova's position in time relative to the Earth can be calculated. Due to the universe's expansion, these supernovae appear to be stretched and move further and further away from us. This also results in the stretching of the light's wavelength, causing it to emit a red light. This is called the redshift. By measuring the change in the redshift over time, we are able to see that it is increasing exponentially, demonstrating that it is continuously being stretched. This increase in the cosmic expansion is strange, as it is against gravity. This demonstrates that some force is acting against it. We call it dark energy, which is unrelated to dark matter. We can also observe this force acting upon the fabric of the universe, as one might call it, with baryon acoustic oscillations. These are patterns of density distribution variations that resemble wrinkles. Initially, during the beginning stages of the universe, matter was relatively evenly distributed from the outward explosion of the Big Bang and its outward expansion, partially fueled by dark energy. Meanwhile, gravity was pulling it all together. What happened is that as the outward energy and the gravity interacted, clusters of matter were formed. As atoms formed for the very first time, they were concentrated and formed more readily in these gravity-induced bubble-like clusters. This may all seem relatively logical. So, what is the connection to dark energy? While observing the formation of these density bubbles, some measurements approved the initial values of dark energy, but some of them point to an evolving dark energy. However, more evidence is needed to draw an appropriate conclusion on this topic. Evidence that, as soon as it is published, will be discussed in another video. Thank you so much for watching. Drop any topic recommendations in the form below and questions in the comments. I hope you've enjoyed enough to like and subscribe. Stay tuned for the next video and have a wonderful day.